ahead and get started. So the topic today is regression, and specifically multiple linear regression. So in a previous session, we talked about simple linear regression. We talked about polynomial regression, some other forms of regression. So we're going to talk specifically about multiple linear regression today, and specifically about multiple linear regression with more than two variables. As part of that conversation, I'm going to introduce the idea of statistical significance in the context, because it's critical for understanding the difference between multiple linear regression and simple linear regression. And then we're going to talk about, very briefly, just how do you evaluate the performance of your regression models once you get them built, and then we'll talk about how this gets used in some AIOps solutions. And this picture over here, you see me outside the office of Amartya Sen, who's a very famous philosopher. Philosophy is a hobby of mine, so I feel proud to be able to say that I took a picture in front of his placard. Okie doke. So let's talk about what regression is. The literal definition is the regression is reversion or towards the mean. And the idea here is that if you have a data set that has a shape to it, right, or a distribution that's somewhat regular, you can establish the mean for that distribution and then create a mathematical model that will allow you to predict it. Now, the way you establish the mean is that you have to look at a specific single dependent variable that you want to predict or you want to model. That's what you call your output, right? And you can use any number of independent variables that may or may not have an impact on that dependent variable. So the whole purpose of regression is to determine which of those variables have an impact, at least in terms of multiple regression, which variables have an impact, how significant is that impact, and then go ahead and create a model for it. And you're going to do a best fit model just like you do with any other form of regression. Now, very important, it sounds like you're proving something here or you're discovering a relationship. What you are discovering is correlation and not causation. So when you say that an independent variable has an effect, a significant effect on a dependent variable, you're just establishing that there's a correlation. When one moves, the other moves. It doesn't necessarily imply causation. I know that's difficult, but you want to make sure that you're just careful that you're not saying that you're proving causation when you're doing regression modeling. Now, the other key point is that you do need to have data to train. So if you look at our previous session, we talked about supervised versus unsupervised machine learning. This is a supervised machine learning task. So you need to have data to train, and you need to have to know what your outcome looks like so that you can create your model. All right, so let's just do a quick reminder, simple linear regression. And simple linear regression is just simply when you have one independent variable and you have one dependent variable, and you look at your data and you see a pattern or a distribution that suggests a straight line. So this is super common in IT operations. This could be resource consumption over time. If you're talking about capacity, it could be not necessarily time series, but there are other IT operations performance metrics that you're used to seeing that show up in this linear way, of course, right? So the thing about this model, it's very simple. It actually uses the equation that you learn in algebra in like junior high school for creating a line. So you have a slope, right, and an intercept and all that sort of thing. It's the same number. And when you look at it, you can tell what the impact of your variable is. First off, you know the variable has an impact, the independent variable, and then you can look at it and you can pretty much determine what that impact is, right? So it's a very, very straightforward model. Now, in multiple linear regression, you have two or more independent variables, and you still have a distribution that suggests a linear relationship. Now, the difference is that you have to discern which variables are significant, and you have to also discern the magnitude for each one of the dependent variables. So right now, this is the last visual I'm going to show you, because it's the only way that we can, 3 dimensions is as much as the human brain can create a visualization for. So in this example that I'm showing you, this is 2 independent variables and 1 dependent variable. You can imagine that the line becomes a plane, right? So that green shaded area is the equivalent of the line that we saw in the last graph. and you can see over on the right-hand side how the model would predict the impact, would predict the dependent variable based on the two independent variables. So you would have sort of a length and a depth location on the plane that would then correspond to a value on the dependent variable axis, right? And the equation is very similar. Just you can do it for any number of independent variables, but I'm showing you for two. So the question for us is, what happens when we have more than two independent variables, right? What do we do? Well, first off, you can't visualize it. There are tools that statisticians use for reducing multiple 3+ variables into a visualization, but we're not going to cover them here today. The point is that all of the representation gets done mathematically as opposed to visually. So what this means is a couple of things. One is it means that you have essentially an unlimited number of variables that you can examine for any given regression model that you're looking at. But it also means that you don't have the eyeball test that tells you that that the distribution looks roughly like this or roughly like that, and which variables to trust. So what that means is we end up having to add a step for multiple linear regression into the process of building a regression model that we don't have to do for simple linear regression, and that is to establish whether or not any given independent variable is significant. And this is a big, big step, and it makes a big difference. And what we're essentially doing is we're going to look at each variable independently. We're going to establish whether or not it has a statistical significance, and there's a mathematical model we're going to talk about in just a second. And if it does, we keep it, and if it doesn't, we ignore it. And the reason it's okay to ignore some of your variables is if they have no correlation to the dependent variable. In other words, changing your independent variable doesn't have any meaningful effect on your dependent variable. You don't need it to determine how to predict what the outcome of that dependent variable will be. You only want to keep the ones that are actually going to help you do the prediction. All right, so let's talk a little bit about significance. And really what we've got here is this notion of p-value, statistical significance as measured by p-value. So what is p-value? P stands for probability. And so this is really an assessment of the probability that the data you're looking at, the variable you're looking at, in this case, the data you're looking at, how probable is it for you to get that as a result if you make a certain assumption about your test data or about your model. So if you make this assumption, how probable is it that you would get this result, right? If the answer is very probable, right, it means that your assumption is probably right or might be right. So it's evidence that the assumption you have is correct. If, however, the data you look at shows that it's not very probable, then what that tells you is that your assumption might be wrong, okay? So when you're using p-value in other sorts of applications in statistics, what you're trying to do is basically validate or invalidate a hypothesis. The way we're going to use it here is slightly different in the sense that we are going to invalidate or validate a hypothesis, but we're doing it specifically for the purpose of establishing what variables we want to keep in our model. So we're not going to modify our hypothesis based on our outcome. We're just going to use it to establish which variables we want to keep. Now, your assumption in this case, it's known in statistics as the null hypothesis. So if you hear the null hypothesis and you're trying to validate or invalidate the null hypothesis, that's what it means. And usually the level of what constitutes not very probable, in other words, where you would have the cutoff of whether you would think of your assumption as being essentially, invalidated or evidence against is 5%. This is just an arbitrary but commonly used threshold. Sometimes in some applications, depending on, you might go as low as 1% or differently. You may increase it. It's a function of, the specifics of the test case that you're looking at. But, typically what we're going to look for is a p-value of less than 0.05 or 5%. All right. Let's get back to our multiple linear regression model. So we have a null hypothesis, and our null hypothesis is that the independent variable that we are looking at, any given independent variable we're looking at, has no significant impact on the dependent variable, right? So if we say our assumption is, yeah, this variable isn't going to do anything for us as a predictor because it doesn't have a significant impact, and then we get a probability greater than 5% that that's true, then we have good evidence that that independent variable is not going to impact the dependent variable, and it's going to be a poor predictor, right? So that's why it's not good for the model, and we want to leave it out. If, however, we get a p-value when we do the analysis of less than 5%, we have good evidence that independent variable actually does have a significant impact on our dependent variable and could potentially be a good predictor of the outcome of that variable. So we're going to keep it in the model, right? Now, you have the basic concept of how we establish and evaluate independent variables. Now, what we do when we build a multiple linear regression model is we have to test each one of the variables, and we have to test to determine whether they're included or not. And then you do work when you include variables to make sure that in conjunction with each other, they also still maintain their significance. So you can look at a variable in isolation, and it might give you one statistical significance rating, but then in combination with other variables, it may look differently. And because the behavior changes, because variables influence each other in the model, you have to test them independently and together, and there's a bunch of different ways that you can do that. I'm not going to go into the details here, but you can, for example, look at them all together simultaneously and then start eliminating. You can do it one by one and measure each one independently and then add it or not add it, build your model up from the ground. You can look at all possible combinations simultaneously. A lot of different ways you can do it. There's not one that's better than another. It just depends on the application, what makes sense. But of course, when you have many, many, many variables, the compute power and time that you would be required to use, it can be significant. So there's some strategies that are more efficient than others, I guess you could say. All right, so let's go back and try to make it a little bit more clear where we're at, right? So let's say we have 7 independent variables that we're looking at in our dependent variable, and we measure the significance, the p-value for those 7 different variables, and we get the values that are listed there in that second column. You'll notice that 4 of them are above 5% or 0.05, and we have 3 of them that are below. So if we were to build our model, okay, we would keep the 3, so x sub 3, x sub 4, and x sub 7. We would get rid of the other ones. Once we did that and we built those 3, we would look at the 3 of them in combination with each other. We'd verify that the p-values maintained their position, that we didn't need to continue to refine by eliminating any of them. Then we can determine also, once we have those narrowed down, we can look at the magnitude of the impact. So some of those variables may move the needle further, like a corresponding jump of 1 unit in x3 might be a corresponding jump of 1 unit in our dependent variable, but for x4, a move of 1 unit might only move the dependent variable by, let's say, half a unit, right? So there's a different impact. It's significant in the sense that there's definitely strong correlation, but the magnitude of that correlation could be different. And then also what we can do is, even though once we've established what those variables are, it could very well be that the model is still not very good, that the fit still isn't very good, and so that the model itself wouldn't be very useful for us. So we still want to look at fit, and if you refer back to the previous webinar, the fit, we use the same measure, which is adjusted R squared. So in the simple model, simple linear regression, you have R squared and you have adjusted R squared, where R squared looks at a single variable, adjusted R squared is for multiple variables. In the case of this, since we have multiple variables from the start, we will only look at adjusted R squared, right? So like I said, we've established what what variables we want to use. We've established the magnitude of the impact. and then we have to just make a final step and we validate that the model still has some utility for us, which in IT is frequently the case because we have very structured and regular data. That's very, the lessons we learn from which and the predictive models we create are very transportable. All right, so let's review what we've learned and then let's look at some examples. So what we've talked about here is a machine learning technique for evaluating a linear relationship between two or more independent variables and the dependent variable we want to predict, multiple linear regression. We've talked about how you have to evaluate whether the variable has a significant impact, which means it's a good predictor and you keep it in the model or you get rid of it. And then having done that and identified the variables you want in your model, looking at both the magnitude of the impact for those variables as well as the goodness of fit or the effectiveness of the model. All right, so let's talk about a couple ways that this can play out inside of AIOps. These are just two examples that we have here at BMC. There are obviously many more out there in the market, but I wanted to talk about this. So in our capacity optimization solution, we have a couple of different modeling capabilities. Well, we have lots of different modeling capabilities, but two specifically. One is called a virtual planner. The other is known as a what-if scenarios. And in both of those cases, what you're doing is you're taking a set of criteria. Think of these as your independent variables. So you might count memory, usage load, saturation point, CPU, bandwidth. I mean, just go on and on and on. And you can essentially use that to model an output around what's right-sizing a migration or the setup of a virtual machine off of physical hardware, or potentially some other type of migration activity. So, for example, if you wanted to migrate, you wanted to create a what-if scenario because you were trying to figure out whether you should move an application from its existing infrastructure just to a right-sized infrastructure of the same type, whether it's larger or smaller, right? You can use it in the virtual planning. You're planning for a move to virtualization, but you can do that also from just existing solid infrastructure to solid infrastructure, or infrastructure or virtual machine into a cloud application, right? There's a cloud services model. So there's a bunch of different capabilities. But in all of these, what you're doing is you're establishing multiple independent criteria, and you're trying to determine an output. Now, I will say that it's not as simple as just doing a single multiple linear regression model. There's actually multiple models that have to be built because your single dependent variable will just establish one aspect of the output you're trying to get here. Like if you're trying to figure out how much memory, CPU, and storage I need, right, from all of these different criteria, you're going to do multiple different models to establish CPU, memory, and storage separately, and then provide them back to you as a package. The second example, which comes from our monitoring and performance management space, is about probable cause analysis. So this one is another one where it's not as simple as just using a multiple linear regression model, but what we do when we do a probable cause analysis inside of TrueSight Operations Management is we are looking at the significance of a variety of independent items on a particular event or on a particular series of events or event storm or timeline. So the idea here is that you look at log data, you look at monitoring data, you look at event data, and you use linear regression in combination with some other techniques to establish which of the elements have a significant impact on the event that you're interested in, and then also establish the magnitude and the prioritization. So the output of a probable cause analysis in TrueSight Operations Management is actually a statistical probability matrix of, in this case, it's correlation, but we're trying to get more to a causation inside of because we use a linear timeline as well, and tell you that we believe, based on what we've seen, that with an 80% probability, this thing is the cause of the event, or this is the precipitating event that caused the event that we're interested in looking at. So as I mentioned, the purpose of this conversation is to discuss different types of machine learning techniques inside the context of IT operations, so we can talk about AIOps use cases. We've talked now about regression in a couple sessions. In the future, might look at some other different types of regression. So we've got those three at the top. I'm particularly thinking logistic regression will be interested for those folks of you that in IT ops that interface with the SecOps side of the house. Logistic regression is very commonly used in security applications because it's similar to multiple linear regression in the sense that you look at multiple independent variables, but you're trying to determine, instead of a continuous output, what you're trying to determine here is kind of an A/B, 0, 1, yes, no kind of output. So that's good for doing things like threat detection, spam, that kind of stuff. And then, of course, we can talk more about non-regression techniques. So classification and clustering we'll definitely get to in the next year. Natural language processing, I'm really interested in doing something with the chatbot, our Helix chatbot. Obviously, we have to talk about time series analysis for doing predictive analytics, and maybe we'll get into neural networks. Okay, so just as a reminder, this is just a little simple graphic on some techniques that we use inside of TrueSight to accomplish use cases like event noise reduction and predictive alerting, et cetera. So you can definitely look at the documentation that we've got out on the web. You can follow my blog series. You can check out our webinars that I've been doing here. And ideally, if you've got questions, please feel free to post them in BMC communities, contact your account manager, contact me, and we'd be happy to discuss. I certainly would also be interested if people would like to suggest topics for next year that they'd like to see. All right. With that, thank you very much.